Hello, welcome back for the final lecture on foreground emission mechanisms as a part of the cosmological component separation course. And this lecture will be focused on free, CO, and CIB emissions. As always, let's refamiliarize ourselves with the microwave foreground gallery. And in this lecture, we'll be focused on the blue free line, the black CO lines found here at 115, 230, and 345 gigahertz, and the CIB emission, which is, has a spectrum similar to that of the thermal dust emission. We'll start with the free or bremsstrahlung emission, which many I'm sure are familiar with, which is given by the acceleration of electrons by protons and other ions in the interstellar medium. And this emission is given by the equation at the bottom of the screen here. So there are multiple terms which we should walk through and dissect here. Obviously, first what we need is the number of protons and electrons to determine the total emission, and to get the total intensity we integrate over the line of sight. So we'll define this and something called the emission measure to help our calculation. This is just the integral of the number of electrons and the number of protons along the line of sight. And this is linearly proportional to the free intensity and the optically thin limit, which we assume here. The radio emission comes from the acceleration in the perpendicular direction, so of E towards P along the motion. And this the change in velocity of our electron is given by essentially the impact parameter B, how close we pass to the proton, 1 over B, and 1 over the velocity. We can reasonably expect that the energy extracted from this electron to go something like 1 over the change in velocity squared, and that this process to happen at the rate of the velocity times the number of electrons times the number of protons. So we have the emission is proportional to the number of electrons times the number of protons over the velocity of our electron. Now, if the electrons have a thermal velocity distribution where V is proportional to V is given by the square root of kT over the mass, then this emission should find our emission is proportional to the number of electrons times the number of protons over T to the minus 1/2, which we see here in the bottom equation. This next factor, the exponent, comes from the assumption that the velocity is Maxwellian distributed, as we have just talked about, and that the photon discreteness effect, i.e. that you can't have photons, or you can't emit any photons with energy greater than 1 over 1/2 mv squared, excuse me. And then finally we have the Gantt factor, which is exactly 1 in classical theory. However, quantum mechanical corrections induce frequency and temperature dependence. In fact, without these, we would expect a completely flat, free spectrum at low frequencies. For free polarization, see that free is not intrinsically polarized, but can occur in H2 regions where there are lots of free electrons available for Thomson scattering. Thomson scattering can impart a linear polarization at roughly the 1% level if you are resolving the cloud, but it cancels if otherwise, which we don't actually resolve individual clouds here. I'm probably going to need high resolution to see this, so it's not a concern, but it is a good thing to keep in mind. Next, we'll move on to the carbon monoxide physics. So let's start with the classical analogy. You have two masses attached by a massless rod, which rotates about the center of mass, as given by this cartoon here with a cyan C and a red O atom connected by a massless bar. And the rotational energy of the system is given by the L squared over 2I on the right here, which of course we can quantize into something given by the angular momentum vector J. And considering this rotational energy, we can emit a photon by making a transition from J plus 1 to J with an energy given by this here. And since J equals 1, 2, 3, which is nice and linear, we get a ladder of evenly spaced CO lines. So the CO emission from the first first excited rotational state to the ground state will be 115 gigahertz, from the second to the first, 230 gigahertz, and so on. Is this CO polarization or CO emission polarized at all? According to the Goldreich-Kjalfus effect, the CO rotational levels are split by the magnetic field, and emission from these levels have equal and opposite amount of linear polarization if the levels are equally populated. But these levels, we don't expect these levels to be equally populated if there are cloud anisotropies, if the environment around some CO molecules is not similar to that of some nearby CO molecules, then there will be some remaining linear polarization. And this has been detected in a couple of cases in specific clouds at roughly the 1% level. Is this a problem for B-mode science is the question here, and this study by Puglisi calculates that this effect may produce a signal in the CMB B-mode power spectrum at the R of 0.02 level, which is something to consider when analyzing data sets where the CO emission is prevalent, like the Planck 100 gigahertz, 217, and 353 gigahertz bands. Finally, we'll talk about the cosmic infrared background, which is shown here in megajances per steradian at 857 gigahertz. CIB is just thermal dust emission from all of the high Z star-forming galaxies that we can't actually resolve, and this is redshifted and perhaps a little higher temperature than the galactic dust emission that we see now, and the density of the power spectrum of CIB as a function of Z is shown in the plot on the right here. CIB is great for cosmology. It can tell us how the clustering of galaxies from different dark matter is different from dark matter, galaxy bias, and can also be largely studied through its angular power spectrum of its anisotropies. But CIB is difficult to actually distinguish from the background itself. CIB is less correlated from frequency to frequency than the galactic dust emission is, and each source is contributing from a different redshifted spectrum. So there is a naive way of making a CIB map, which is just to find the best fit scaling factor between the Planck maps at two frequencies, given by the thermal dust SED, for example, and subtract one from the other, and the residual will have a lot of CIB. Not only CIB, but a lot of CIB. We could also use H1 as a spatial template for galactic dust, and you can use that frequency information to apply a temperature correction. Lens Plus has done this, I believe, in 2019, making CIB maps using this H1 correlation, which we see here. We also, from a cosmology perspective, we can look at the CIB as how it correlates with CMB lensing to see if there's a correlation between the lensing of the CIB or the CMB and the power of the CIB, and we can see which is shown in this plot here. So overall, what we have is that the free is a well-known SED. It's unlikely to be polarized at significant levels, and CO may be polarized at a few percent, but maybe enough for us to worry about, but only at very, very specific sharp frequencies. And separating dust, whether it's extragalactic, separating extragalactic dust from galactic dust can be difficult, but the H1 dust correlation can help